Hello students of Year 12 General Maths and welcome to exercise 7D of your textbook, which is effective annual rate of interest. Now before we get onto this new topic, I'm just going to give you a few reminders about simple and compound interest and the differences between them.
So simple interest is when a certain percentage of the original value of something is added to it each time period. The original value of something, it would never change over time. So that means simple interest is constant. So if I get $100 worth of interest in my first year, the second year will also receive $100 worth of interest. And that value will never change, the same amount of interest every time period. Therefore, it's constant. Now, compound interest is when a certain percentage of the current value of something is added to it each time period. So because the current value does change, obviously because we're adding interest to it, compound interest is actually exponential because not only is our current value changing, but that means our interest is also changing. Both of them increase at the same time. So if we take a look at this next slide here, here's a little visual reminder of what that difference means for us. So the orange line represents simple interest, and it's just a straight line with a constant gradient the whole way along, because the difference here is the same amount of time and the same amount of money as this distance here, roughly. So that means every single year we get the same amount, or every single month we get the same amount. Now for compound interest, we actually have an exponential line which gets steeper as we go further on because, like we said, both the current value of our investment is increasing or our loan is increasing, but that also means the amount of interest we get will increase as well. So because both of them are increasing and both of them increase each other as well, we get exponential growth, which will just tend off higher and higher and higher as the blue line shows. Now, another reminder is the concept of compounding periods. So when our interest compounds, that is when we collect the new interest and we add that into the account or the loan as well. And then we now start calculating our interest based on that new amount. So I might get $10 of interest on my $100 loan, and now I've got $110 in the loan, and my interest next period will therefore be even higher than the original $10. So let's just remind ourselves that interest can be compounded according to different periods. So daily, weekly, monthly, yearly, etc. Theoretically, you could do anything you wanted to. You could do every second is a compounding period. It's not very realistic. It's hard to find a practical situation where that's represented, but it is possible to do the calculations. Now, as a general rule, this might be obvious to some, the more often interest compounds, the greater the final value of the investment or loan will be. Okay, so the more often we compound, the more often we increase our current value, and therefore we increase our future interest as well. So the more often we get to do that, the steeper and steeper our line will get faster. So another way of saying that is that if all other variables are equal, and by those I mean the principal, interest rate, and number of time periods, then monthly compounding periods will always be better than yearly because there's more months happen more often. Weekly compounding periods will always be better than monthly because weeks happen more often than months, and so on. So the more frequent the period is, the better for a compound interest loan or investment. Now here's an example of that concept in action. So this table here, it shows 12 months along this left-hand column here of an investment of $5,000 that has an annual interest rate of 4.8%. Okay. Now this second column here represents the compounding period of just once per year, so a yearly compounding period. And because this is only 1 year, that's equivalent to simple interest because it never gets to compound more than once. So at the end of the year, if we grow by 4.8%, the $5,000 is turned into $5,240. And that, like we said, represents 4.8% interest. Now, there's a few more columns in this table, and each column shows us what would happen with a different compounding period. So now in this next column, instead of 4.8% per annum, we're doing a quarterly interest compounding rate where we divide the 4.8 by 4 because there's 4 quarters in a year, and we get 1.2% per quarter. So that means we compound a few times over the year. So after 3 months, we've compounded to $5,060, then 6 months, we get $5,120.72, and so on till the end of the year where we finally receive that last interest payment, and we're now at $5,244.35. Now, obviously, that amount is better than the amount in the previous column. It's higher by $4.35. So having quarterly compounding periods better than yearly. Now, the same principle happens again over here with our monthly column. We've got the 4.8% per year, but we've divided it by 12 to get to a monthly amount of 0.4% per month. So our $5,000 turns into 5,020, then 5,040, and so on until we eventually arrive at $5,245.35. Now we notice, again, that's better than this value here in the preceding column by another dollar. So what that means is if we increase our compounding period, so we increase the frequency of our compounding period, we'll just continually get better returns on our investment. Now, what we should realize down here is this very bottom row. It's starting to talk about the effective annual interest rate. Okay, so this $5,244.35 in my middle column, if instead of quarterly compounding periods, instead, if I wanted to get that same return on my $5,000 original, if I wanted to get that same return with only one compounding period per year, this row here is telling me that I would need a 4.89% interest rate. And likewise, in my final column, if I wanted to replicate the growth of $5,000 turning into this amount here, the $5,240.35, if I wanted to replicate that with just one compounding period, I would need an interest rate of 4.91%. So that's something that effective interest rate can show us. That is what the definition of it is, essentially. And that's what this slide here says. I'll read it out to you once again in a slightly different phrasing. This slide says that the effective interest rate tells us the equivalent simple interest rate that a given compound interest loan or investment would require in order to grow by the same amount in 1 year. Now, the way we calculate the effective rate of interest is with this formula down here. This formula is on your formula sheet, so memorizing it is not something you have to do, but you do need to know what it is, what's it for, what sort of questions will require it, and where would you find it in the formula sheet. So it says that the effective interest rate, that's this I effective subtext here, is equal to the number 1 plus lowercase I, the annual decimal rate of interest, divided by the number of compounding periods, which is this n, and that's in brackets, and then we raise it to the power of n as well, which is the number of compounding periods per year. So what that means is if the number of compounding periods was, if my compounding period was months, then n would equal 12. If it was quarterly, then n would equal 4, because that's the number of times a quarter happens per year. And after I do that calculation, I then subtract 1 as well. So it's 1 plus I over n in brackets to the power of n, all subtract 1. Alrighty, let's take a look at why we would bother to use this effective interest rate. Now, the reason I would choose to use it is because if two different investment or loan options have more than one variable that are not in common with each other, so that means maybe I have different compounding periods and I have different interest rates for the two loans, it's actually really difficult to decide which is a better option. So for example, I could be thinking, do I choose this 5% interest rate that compounds once, or do I choose the 4.8% interest rate, which compounds twice per year? Which one's better? They have different interest rates and they compound a number of times per year. So it's not really easy to choose which one is a better option just by sight. I'd have to do a bunch of future predictions of values with the compound interest formula. Effective interest rate allows us to skip that. So it allows us to make a comparison by seeing which option will experience a higher percentage growth in just 1 year, because that's what the effective interest rate is. It tells you what percentage growth does the original grow to by the end of the year if there was only one compounding period. All right, let's take a look at an example question here where we use effective interest rate to compare different loans or investments with each other. So this example says Brooke would like to borrow $20,000 and she's deciding between two loan options. So she wants to borrow $20,000 and her options are a 5.95% per annum, which compounds weekly. Now, the second option is 6% per annum, so a better interest rate, but this one compounds quarterly, so it compounds less often than the other loan. So one has a better rate, but less compounding, and one has a worse rate, but it compounds more often. Like we said, it's difficult to decide which is better straight away. And we want to calculate, so to answer this question, we need to first do part A, which is to calculate the effective annual rate of interest for each investment, and then we can decide which is best and why. So let's do option A first. Option A was 5.95% per annum compounding weekly. So I need to use my effective interest formula in order to calculate its effective rate of interest, obviously. So I'm going to write my formula first. It's 1 plus I over n, all to the power of n, minus 1. Now in this case, obviously 1 stays the same. My interest rate, is 5.95% turned into a decimal. So that's 0.0595. My number of compounding periods per year, it's weekly, so that's 52 weeks per year. Now, the same number is the power as well, because it's n on the bottom of that fraction and n is the power. And then I subtract 1 from that. Now, of course, our calculators are quite smart. They can handle all of that in one step as long as we type it in correctly. So I'm going to do that. 1 plus 0.0595 divided by 52. And I'm putting that in brackets and raising it to the power of 52. And then subtracting 1. And my answer here is 0.06127. Alrighty, 0.06127. Now I'll turn that into a percentage as well, just to make it easy to think about. So that's a decimal. I have to times it by 100 to turn it into a percentage. And that equivalent percentage is 6.127%. Alrighty, so that's my effective interest rate for the first loan. So that's saying that my $20,000 will grow by 6.127% over the course of that year with that loan. So let's take a look at option B now. Now, option B, I used my same formula. My effective interest rate is equal to 1 plus the interest rate as a decimal over the number of compounding periods to the power of the number of compounding periods minus 1. And in this case, that means it's 1 plus 6% as a decimal, so 0.06, over 4, because I'm a quarterly compounding period now, to the power of 4 minus 1. Again, I'll do it in one step on my calculator. So in brackets, 1 plus 0.06 divide 4 to the power of 4, subtract 1. And now my answer is 0.06136. Sorry about that. So I like to go to 5 decimals here because it gives me, when I turn into a percentage, that gives me 3 decimals. So let's turn that into a percentage now. It's 6.136%, roughly, because I have rounded that number as a percentage. So that's part A. I've calculated the effective annual rate of interest for each of those investments. And now B says which investment option is the best and why. Now, in this case, this is actually a loan that Brooke is considering. So Brooke's not considering investing her money. She's deciding between 2 loan options. So because it's a loan, she actually wants the lower interest rate here because she wants the loan to grow by a lesser amount per year. So if I'm answering B, option A is better. Option A, better option. As the loan will experience less growth. And that's due to its lower effective interest rate. Alrighty, thank you, Year 12. Good luck with these exercise questions.